Welcome to This Explainer. Today, we're diving into the sheer technical magic that makes real-time, photorealistic graphics a reality. We are talking about the absolute cutting edge of visual fidelity, that sweet spot where computer science literally hacks human perception. Let's unpack exactly how developers pull off this mind-bending feat.
In the high-stakes world of virtual reality, 20 milliseconds is the magic number. It is the absolute maximum threshold, what's known as motion-to-photon latency, needed to maintain total, unbreakable immersion. If a system takes even a fraction longer than 20 milliseconds to render a frame after you move your head, the whole illusion shatters. And worse, you'll probably start feeling physically sick.
But here's the massive challenge we're facing. Modern neural rendering relies on insanely complex artificial intelligence and deep learning to synthesize these gorgeous visuals. It is incredibly computationally heavy. So, with all that immense computational weight, how on earth do developers actually achieve this lightning-fast, ultra-low latency?
Well, here's our game plan to find out. First, we'll look at the neural rendering revolution. Second, the latency bottleneck. Third, memory management under the hood. Fourth, how modern C++ to the rescue. And finally, achieving ultimate rendering performance.
Let's kick things off with Section 1, the neural rendering revolution.
Just think about how unforgiving these latency budgets truly are across the board. To deliver true immersion, modern gaming is strictly capped at a 16 millisecond rendering budget per frame. VR, as we just mentioned, caps out at 20. But augmented reality? That demands an incredibly strict sub-10 millisecond response time to convincingly blend digital content into the real world. It's a blisteringly fast turnaround.
To hit these speeds, tech giants are aggressively attacking the challenge from two angles at once. Companies like Microsoft and Intel aren't just slapping bigger chips into machines. They're combining specialized hardware acceleration, think Microsoft's Azure Cloud Edge Hybrid or Intel's Z GPU architecture, with incredibly deep, low-level software optimization using tools like DirectML and the OneAPI framework. Hardware alone won't save us here. The software has to be meticulously optimized.
Which brings us right to Section 2, the latency bottleneck.
So what's actually slowing these powerful systems down? Well, the biggest villains are neural radiance fields, or NeRFs, which can demand hundreds of complex neural network calculations for a single pixel. We also have redundant ray sampling and CPU-GPU synchronization issues causing latency spikes. But the absolute biggest bottleneck squeezing the life out of these pipelines, memory bandwidth. We're talking about massive constant transfers of data between GPU and CPU memory. If that data isn't managed perfectly, the whole system chokes. Let's dive deeper into that in Section 3, memory management under the hood. To solve this bandwidth crisis, elite software developers have to absolutely master advanced memory management. When you're dealing with millions of calculations every single second, modern C++ provides the most unparalleled control over memory allocation. But, as you probably guessed, with massive power comes massive risk if you handle it wrong. Under the hood, C++ gives developers a choice between two main memory types. First, you have static memory. It's fast, fixed in size, and safely managed by the compiler. Nice and easy. But for complex neural rendering, where data sizes constantly change depending on where the user is looking, developers have to rely on dynamic memory. Dynamic memory is allocated on the heap during runtime. It gives you incredible flexibility, but traditionally it requires explicit manual management from the programmer.
And if dynamic memory is handled poorly, it acts like a dripping faucet that eventually floods your entire house. You get memory leaks, where memory is never freed and just eats up your system resources. You get buffer overflows, dangling pointers, and double deletions. Any single one of these issues will instantly ruin your frame rate, freeze up your VR headset, or completely crash the application.
So how exactly do developers safely harness this incredibly powerful yet dangerous dynamic memory without bringing their photorealistic worlds crashing down?
That is exactly what we'll answer in Section 4, Modern C++ to the Rescue. In the old days, developers had to manually allocate memory using the new operator. Use it, and then flawlessly remember to free it using delete. Sounds pretty straightforward, right? But when your engine is executing billions of operations just to draw a room, forgetting a single delete command inevitably leads to those catastrophic memory leaks we just talked about.
Enter a brilliant concept called RAI, which stands for Resource Acquisition is Initialization. This is a foundational programming paradigm in modern C++. Instead of manually calling delete, RAI ties the memory directly to an object's lifecycle. So the exact moment a resource goes out of scope, it is automatically cleaned up.
This RAI paradigm completely revolutionized things, shifting developers away from dangerous raw pointers, which require manual cleanup, and over to smart pointers. Smart pointers essentially act as automated, fail-safe guardians for your memory.
By utilizing a smart pointer, specifically something like standard unique pointer, the need for manual deletion is completely wiped out. The unique pointer takes exclusive ownership of the memory, and the split second it goes out of scope, the memory is instantly and automatically released. It safely seals up potential memory leaks for good, saving those ultra-precious processing cycles.
Let's bring it all together in Section 5, Achieving Ultimate Rendering Performance.
Achieving that sub-20 millisecond render time is really a beautiful symphony of hardware and software. Developers have to harmonize raw hardware acceleration, like specialized GPUs and tensor cores, with predictive caching algorithms, adaptive quality scaling, and that flawless C++ memory management using RAI and smart pointers. By automating the memory management, the system is finally free to focus purely on blasting out those high-fidelity graphics without bottlenecking.
This incredible combination of hardware and software is what lets us step into perfectly rendered, immersive digital worlds today. But as we continually push the boundaries for even greater photorealism and even deeper neural networks, you really have to wonder, will our physical hardware eventually hit an absolute wall? Or will the brilliant software optimizations of tomorrow continue to save the day? It is an absolutely thrilling frontier. Thanks for joining me on this explainer, and we'll catch you next time.